right, so this week we're going to be talking about logistic regression, and don't forget that these are bonus assignments are due if you're interested in doing that. Now, let's see what logistic regression is, and let's get to the notebook. So, all right, so what is logistic regression? Logistic regression is used for predicting 0-1 variables for binary outcomes like life or death, success or failure, getting an A in this class or not getting an A. So we haven't done that yet. So far, all the variables that we've been predicting have been quantitative. In other words, if I asked all the ones that we've used as Y variables, could be, the answer is a number or a category that has more than 2 variables, more than 2 outcomes. But what if you only have 2 outcomes, like yes or no? Then how could we use our ordinary least squares regression equation to make a prediction for just a 0 or 1? That kind of doesn't really make sense. We'd have to, what makes more sense is the best we can do is make a model that predicts the probability of getting a 1 or a 0, given a set of predictors. All right, so here we have this real data set that is based on 55 students who are applying to medical school. And on the x-axis right here is their biological science score, and on the y-axis right here is whether or not they got accepted to medical school. Well, as you can see, each person got either a 0 or a 1. Now these little dots, some of them represent more than one person, as you can see, because we don't have 55 dots here. But everybody got either a 0, they got a no, or they got a yes. So how would we, this right here is the least squares regression line that was fit by minimizing the sum of the squared errors. Well, what did it minimize here? How was this arrived at? How was this equation arrived at? So to show you, let me go to the data program here. So let's go right here. And if we look at our data program here, and we are predicting the Y variable acceptance based on a biological science score. And now you can see that there's a number of, there's 55 points total here, but everybody got 0s or 1s. And now we look at this regression line right here. And how did it, that's the same one you have in your notebook. And let me show basically the intuition behind how it was arrived at. And that is, remember, if we divide up the x-axis into these vertical strips here, for example, look at number, everybody, there's one, let me put some more jitter so you can actually see what's going on there. Okay, so there's 3 people who got accepted and 1 person who didn't. So that's why this line right here is at 0.75. And same for all the lines here. Here everybody got, people who got 6s and 7s didn't get accepted, so we just have these horizontal lines through 0, and here we have these horizontal lines through 1 because the 1 person who got a 13 and the 1 person who got a 14 got accepted. So this regression line is the best fit through all these horizontal strips here. That's the idea. All right, so you can see, let's go back to our document camera now, and you can see that there's a problem here because it's making predictions. This is probability right here, and it's making, this is the probability of getting accepted here, and it's making predictions bigger outside the range of probabilities, bigger than 1 and less than 0. It does okay in the middle, like for example, for 10. For somebody got a 10 here, we get a 58.5%, which is just, I'm not to figure it out exactly rather than just looking at it right there. I'm just using the equation here, the least squares equation, and plugging a 10 in, and I got 58.5%. But what happens if, on the ends here, like for 6, we can see the line would give a negative probability. And for 14, we can see it's going to give more than 100%, more than 1. So let's try it for 6, and we get negative 1.263 plus 0.1848 times 6. And you get a negative number here, negative 0.154, or negative 15.4%. That's right down there. And of course, that's wrong. That's a big problem. And same for 14. If we did it for 14, we're going to get over 100%. So when I did that, I got 1.432, or 143.2%. Okay? So this right here, these don't make sense. They don't make sense. So linear regression, doing this, linear regression doesn't work. Because it's yielding, because it gives probabilities. Probabilities outside, gives probabilities greater than 1 and less than 0. Okay? Gives probabilities greater than 1 and less, in the range we're interested in, not in some, in the range where we actually have the X scores. And probabilities have to be between 0 and 1, or between 0% and 100%. All right? So this regression line does not work. So what are we going to do? Well, let's turn the page. What we can do is fit, what we really want to do is fit a curve that's bounded, that doesn't go beyond 1 or 0. So it's bounded between 0 and 1. That's really what we want to do. And so this is the proportion of the probability of yeses. And that looks something like that. It does a much better fit, as you can see, except for maybe this point, but it does a much better fit than the line. So you can see on the program here, if we go back to our data program, and we can look at this, and if we fit, we're going to learn how to fit this curve, this logistic regression curve, that does a much better job here than our ordinary least squares fit. Okay, so let's go back to the document camera. And so we want to fit an S-shaped curve. This is what we want to do. Well, there's many S-shaped curves similar to the one above. Which one do we want? I mean, actually, any curve of the form what? Y is equal to some function of x that's positive. It's going to, and then it's increasing, or we could have one that's decreasing, either direction, that has this kind of shape, would work. Like basically any curve f of x over 1 plus f of x, where f of x is greater than 0. That would work. But we pick this, we pick the logistic regression curve is of that form, with f of x being this exponential function, e to the beta naught plus beta 1x for simple regression. Okay? So, because it has some nice features. And we'll explain that in a minute. But first of all, is it bounded between 0 and 1? Can this equation ever yield a probability greater than or equal to 1? No. Why? Because the numerator is less than the denominator. That's because e to the anything right here is going to be less than 1 plus e to the same exponents. All right, so the numerator is less than the denominator. And can it ever yield a probability less than or equal to 0? No, because e to anything is going to be greater than 0 for all x. E to the x is greater for all x. I mean, even if you had a very small negative number as x went to negative infinity, e would get closer and closer to 0. You know, the limit of e to the x as x goes to negative infinity gets tinier and tinier and gets bigger, gets negative infinity gets to be a huge negative number, then you're going to get 0, close to 0. Limit will be 0. So it's always going to be greater than 0. All right, so it works, but it also has another really nice feature besides yielding probabilities between 0 and 1. The other really nice that we just talked about, the other nice feature is that you can transform it into a linear equation. You can transform it into our usual, intercept plus a slope. For 1x, we could add multiple x's by taking the log odds. All right, so if you have this probability function, we can transform the probability into an odds. So the odds is equal to p over 1 minus p, success over failure. And then if you took the log of the odds, you get the exponent. So basically, there's these 3 forms to this logistic regression equation. There's the probability form that we just talked about, which is the S-shaped curve. Okay, we've got that, and we said that's bounded between 0 and 1, and it looks something like that. Or it could be negative, too. It could look just like the flip of, the reflection of that across the vertical axis. So, the other way. For example, if you were, this would positive is, in the example that we're looking at, the higher your score, the more likely you are to get into medical school. But we could do something else like, I don't know, the lower your GPA. We could say the more you drink. Let's say, if that was true, the more you drink or the more you party or something, maybe the lower your chances. Okay, so there's that. And then, let's see, then the odds form. The odds form is what? Odds is success getting into medical school over not getting into medical school. And that would be an exponential curve. That's just this right here, this function, which would look like that. And then you can take the log of that, which is just this exponent right here, and now you get a straight line that is unbounded. It goes from positive infinity to negative infinity, like that. So this odds right here is p over 1 minus p, and this probability is equal to the odds over 1 plus the odds. Okay, and so you can go back and forth between these 3 forms. So it's, if you start with this probability right here, then you could take the odds by taking this over 1 minus the same thing, and it simplifies to that. just like we said to the exponential curve. So this is your S-shaped curve. And then it would simplify if you just, by algebra, just did that, you simplify to this, which is the exponential curve. And then you take the log of that and you get a line. Or you could go the opposite direction, too. So I think it's easier just to do this with examples rather than this algebra, which is it's the same thing. But let's just go through the examples. Okay. Just so you get a feel for it. All right. So this is called the log odds. It's log base E of the odds. And for example, if your odds are 4, this means the probability of the event occurring is 4 times more than that of the event not occurring. People often call it 4 to 1 odds, okay? So if your odds are 4 to 1, what's P? So let's say your odds are 4 to 1. So what does that mean? That means 4, you can think of 4 could be the number of successes and 1 could be the number of failures. What am I talking about here? Let's look. Odds are P over 1 minus P. So how do we define P? We define P as usually the number of, you can call either one success. It doesn't matter. Just call one of them success. It doesn't have to necessarily be a good thing, but you call, and the other outcome is failure. So let's say you just have 2 outcomes. So in this case, we're calling success getting into medical school. So it's probability of success is the number of successes divided by what? The total number of outcomes. Right? And then 1 minus P is the number of failures, because you can only have success or failures, right, over the total number of outcomes. So when I'm talking about the number of success over the number of failures, all I did was I just simplified this by crossing these out. They cross out, and you get the number of success over the number of failures. Okay? So when you say you have 4 to 1 odds, you can think of 4 successes over 1 failure. Okay? So then, if your odds are that, what's P? So your odds are this. That means P is equal to what? Well, P is equal to the number of successes, 4, over the total number of outcomes, 4 plus 1, which is 5. So how about if your odds are 1 to 4? So if you have odds are 1 to 4 odds. I know this is, lots of you who gamble know this very well, but maybe other people aren't as familiar. Okay? So odds are 1 to 4. That means your odds are 1/4. That's your success, number of successes, and that's your failure, number of failures. So that means that the probability is what? 1 success over 5 total outcomes. 1 over 4 plus 1. Okay? So we can do this with all of them. What if your odds are 1/2? Then the probability is equal to what? 1 over 1 plus 2, which is 3. If your odds are 2 to 1, well, then your probability is 2 over 3, etc. So you're going to have some homework on this, but I think you get the picture now. If your odds are 2/3, 2 to 3, then your probability is equal to 2 over 2 plus 3, which is 5. Okay? Another way to describe this is that, why is it the same thing as this, what we're doing? it is. You can see, maybe I should just show you here. You know that odds are p over 1 minus p, and then you can then solve and say p is odds over 1 plus odds, but let's show you how it's exactly the same thing. Here, I could just rewrite this. So this is the same as what? Odds is equal to, I could just say 0.5 over 1. Let's just think that. So then the probability would be equal to 0.5 over 1 plus 0.5, which is equal to 0.5 over 1.5, which is equal to 1/3. It's the same thing. Okay? Exactly the same thing. It's just... All right, so you can think of it this way. That's the formula for it. All right, and now let's see what we should do. Why don't we just fill in this table? And you have a table like this on your homework. I'll post the homework as soon as class is over. And let's just go through this. So this will help you understand it. It just gives you, I mean, after you do it for a while, just muscle memory. It's very easy. Okay, so if your probability is 1 over 100, then 1 minus p is going to be 99 over 100, right? And then your odds are going to be what? 1 over 100 divided by 99 over 100. You cross out the hundreds, and it's 1 over 99. And then your log odds will be negative. You'll have to do this on the calculator, negative 4.6. Okay? And then if we went to the reciprocal here, we could do this. Let's say the probability was 99 over 100, then 1 minus that would be 1 over 100. Then your odds would be 99 to 1. And then the log of the reciprocal would just be the opposite sign. So this is 4.6. And let's look at what happens right in the middle here. If you have a 50-50, if you have probability of 1/2, that's a 50-50 chance, right? So your odds are, your probability of failure is 1/2. 50-50 is 1 to 1 odds. You probably knew that. And then you know that the log of 1 is 0. So you can see that it's symmetrical here, as basically probabilities can go down to 0 and up to 100. Same with 1 minus p. And then your odds, as you can see here, can go down to 0. They're always going to be positive. But it can go up to positive infinity. And then the log can go down to negative infinity and up to positive infinity. And so if we drew their curves, we have this one, log odds, right here. If that's the y0, it can go from negative infinity to positive infinity. And when you have 50-50 chance, it's going to be 0, right? And the odds range, this is that exponential curve, and it ranges from 0 to positive infinity, right? And right at 1 is where you have a 50-50 chance, 0 and 1. And for probabilities, they range from, so here we have this, okay, so probabilities range from, maybe I'll put it over, I can put it right here, between 0 and 1, and they have that S-shaped curve. It's supposed to be an S, and right here is 0.5, right in the middle. So 0.51, right? And your probability is equal to your odds over 1 plus the odds. So in this case, well, we'll start with the odds. and the log odds. So we have an equation for a line here with the log odds. And so it's an intercept plus a slope times x. But then when we take the odds, right, just raise both sides to e, anti-log both sides, and you get this linear equation is now an exponent. Here it's the linear equation. And then when you get the probability, you get the odds, which is e to the, that's our f of x function, over 1 plus f of x. All right, so there's our three equivalent expressions, but we're going to get these betas by doing something very similar to least squares. We're going to do a maximum likelihood estimate to get these betas here, and then we're going to use them in here to figure out probabilities. How about, do I need to fill in the rest of this? I don't think so. You can fill this in on your own, can't you? Does anybody want me to fill it in? Raise your hand. I could do it if you want. You're going to be doing it for homework. It's pretty easy with different numbers. Okay. Just make sure these are reciprocals, right? I mean, not reciprocals. These are reciprocals. These are opposite signs. Okay. I think that's the idea. Now, let's make these predictions using, okay, so what we're going to do is we're going to make predictions for the probability, but we're going to start off with the computer giving us this equation. And then from this equation, we'll compute probabilities. All right, predictive probabilities. So back to predicting the probability of getting into med school. So now we're not going to do it by least squares equation. We're going to do it by this log odds equation here. So now the computer is going to give us these values that instead of doing a least squares fit where you minimize the sum of the squared errors around your model, what it does is it maximizes the likelihood of obtaining what we got, our sample data. That's called maximum likelihood estimates. And for ordinary least squares, they're the same. But they're not the same when we have a 0, 1 y variable. Okay? So this is explained on page 210, so we can just quickly look at page 210. We'll talk about it more later, but let's look at it now. So if we go to page 210, right here. So this is the part I'm talking about. It's a very brief explanation. But basically, the main difference between these ordinary regression that we've been doing and the logistic regression is how we estimate those betas. So instead of doing the least squares estimates, what we do is we choose the betas that maximize the likelihood of getting our sample data, and which is the same as minimizing what's called the deviance. This is explained, you know, where I can show you if you really, some of you are probably very interested in this if you're also taking 400 or 410 because you're probably learning a similar thing. So see, for the mathematical explanation, see week 13 in our pre-R course. So let me just show you how to find this now. You want to go to the lessons page. It's on our course website. Let me just show it to you quickly so you can read more about it. So here, let's see. All right, so if we go here, this is just our home page, okay? And you go to the very bottom, and if you want to become more fluent in R, I've always said you have this free course. We used to offer it as a supplement to Stat 200, and now we're just doing it as a free course, so anybody who wants to can take it. So you can go there, and it actually is kind of cool because you can go to the lessons page here. It's very well organized, and it goes along with, actually the reason we discontinued it is because we had to change Stat 200 to make it a start at the very beginning. This used to be a second semester course, and this went along with it. But it's no longer a second semester course. It doesn't have any prereqs. So we had to, that's why we can't do this anymore. But anyway, if you go down to week 13, which is the end of this course is exactly what we're doing now. So this is exactly what we're doing now. We are in week 13, and we're doing these maximum likelihood and logistic regression. So if you click right here on this, both of these, you'll get a very full explanation of what it's about. All right, so that's how you can find out more about it. Meanwhile, just the quick explanation is what? The quick, sort of more intuitive explanation is that, so we have this thing called deviance here. So minimizing the deviance in logistic regression is analogous to minimizing the sum of squares errors in ordinary regression. It plays the same role. In fact, we have this little, you can make an analysis of deviance table that's just like our ANOVA table. And let me show it to you. Right here. So we have this analogous, and we have this analysis of deviance table right here on page 203. That's analogous to our ANOVA table. All right? It's completely analogous. For example, you get this R squared right here. It's going to be like, instead of this, oh boy, this is so small. Sorry. This is what I'm looking at right here. Okay. So right here is like our sum of squares model. And usually we had R squared as sum of squares model over sum of squares total. What's similar here? 22.54 over 75.79. And you get this sort of equivalent R squared here. That's the same as that. And then you get this, the sum of squares model here, which is really not sum of squares, it's the deviance. You know, it's the structure is very much like the ANOVA table. But this right here is, we wrote it as a chi-square here, but it's not really a chi-square statistic. It's distributed as a chi-square statistic. So this right here is, this chi-square is a sort of modified chi-squared. Basically, this is distributed as chi-squared with p minus 1 degrees of freedom when the null is true. When null is true. Okay. And when the null is true is just that we have no model, right? That our beta 1 is 0. Okay, so that's the idea here. I'll talk about it more later when we get to that part. But for now, what I want to do is just show you how to make these estimates using not our regression equation, but using right here what the logistic regression gives us as estimates for our intercept and our slope right there. So this is the equation right here that we've got. Okay, so we've got that, and it's right here. All right, so what are we going to do? So we're going to start with this linear equation right here. That will be our first step. Then from there, we'll get the odds, and then we'll get the probabilities. Okay? So we'll just follow those steps. And you'll see that the estimates that we get, and we'll compare them to we'll see what the estimates that the logistic regression gives us, and we'll compare them to those crazy estimates we got that with the linear regression, where they went over 1 and under 0. So we'll compare to page 199. So this is pretty simple. So we'll just start right here with our predicted log odds is equal to negative 12.2 plus 1.276 times 10. And here I get 0.56. So now I want to change that to the odds. Okay, so now we want our predicted odds. That's step 2 is going to be e to the 0.56, just following along. And then this is our log odds, and we're just anti-logging. And I got 1.75. Okay, so now I have 1.75 odds, and now I just want to get a probability, the predicted probability, which is step 3. Well, that's just odds over 1 plus odds. So this is equal to 1.75. You can think of it as 1.75 over 1 and just do what we've been doing over 1 plus 1.75, right? And when I did that, I got 0.636, or 63.6%. A little bit higher than what we got on page 199. But now we'll get much more reasonable estimates for this. You'll see that they can't go negative or over 1. So we can do the same thing for this one. So we'll get the log, predicted log odds is equal to now negative 12.2 plus 1.276 times 6. And I got a negative 4.544. So that means the odds will be less than 1. Remember, this is less than 0. That means our odds will be less than 1. Our probabilities will be less than 50%. So we've got negative log odds. So then the odds, step 2, is equal to e to the negative 4.544, which is 0.0106. That's what I got here. So we have this, and now we're just going to get the probability is what? This is step 3, is that 0.0106 over, you add 1 to it. And I got a very small number here, which is what? 0.0105 or 1.05%. Can you see this? Is this too small for you? I'm just going to, can you read this, guys? Okay. And now the same thing. I don't have to keep doing this, do I? Can I just tell you the answer here? The answer for our predicted probability here, these are all predicted probabilities, is 99.65%. Okay, so you can do it on your own if you want. Any questions? All right, it's just the same thing. Now, at what BS score do you have a 50-50 chance of getting accepted? How would you have to start with the log odds. So you use the log odds equation. And what is that equation? The log odds equation, we have to use this. Negative 12.2 plus 1.276 times the biological science score. All right, so what if you have a 50-50 chance of getting accepted, that means your log odds is what? If you don't see it right away, remember 50-50 chance, that means your probability is 0.5. which means your odds, well, this is odds, 50 odds is equal to 1 to 1, 50 to 50, 50-50 chance. And that means that your log of 1 is 0. So when this is true, so a 50-50 chance will just set log odds equal to 0 and solve for the biological science score. So that's what we'll do. So when there's a 50-50 chance, that means the log odds is 0. So we have 0 equals negative 12.2 plus 1.276 times the biological science score. And so that means the biological science score is equal to 12.2 divided by 1.276, which is 9.56. That's not an actual score. I don't think they gave decimals like that. But that should be 9.56. Let's see, is it right in the middle of the curve? Let's see. When you have a 50-50 chance, that would be right here. So it looks like it's 9.56. 50-50 chance. It's less than 10 and bigger than 9. That's what we're doing. Okay? Does that make sense? All right, this is a 50-50 chance, and we just solve for what that score is. Okay, let's see what else we need to do. All right, so let's look at this curve here, and let's interpret the slopes here. And, all right, so do you see how the sign of the slope in the log odds equation tells us whether the probability is increasing or decreasing? So we've been looking at it where it's increasing. We have a positive slope. If it was decreasing, we'd get the same thing with the negative slope. And the magnitude of the slope determines the steepness of the curve. And look at this. The steepness varies across the curve, and it's least steep at the ends and most steep in the middle. Most steep right in the middle in both directions. By the way, this beta knot just shifts in this direction. We're not, as usual, we're not very interested in the intercept. It doesn't change the shape of the curve or anything. It just shifts it in a horizontal direction. All right, so here's our three forms. And what we're trying to look at is this slope in the three forms. And the odds form right here yields the most intuitive and useful explanation of the slope. All right, so let's think about that. Let's think about what the slope means in each one of them. Here, in the one that we have, here it's easy to interpret. This is our usual, this is what our maximum likelihood estimate gives us, 1.276, and it means that for each extra point on the biological science exam, the log odds increases by 1.276. That's not usually helpful to most, certainly not to me, but even to most people, it's not very helpful intuitively to have an increase in the log odds. This is much more helpful, for me at least. It means that for each extra point on the biological science exam, the odds of getting into med school are multiplied by this e to the slope right here. And this is called the odds ratio, which is used all the time. It's the multiplicative increase in the odds for 1 unit increase in x. So if you go up 1 point in your biological science score, you multiply your odds of getting in by e to the 1.276. I mean, this is pretty easy to see. So all we're saying is it's just simple algebra. When x goes to x plus 1, then you have this e to the There's your intercept, e to the b0 plus b1x is going to go to what? E to the b0 plus b1 times x plus 1. And you can see how that is a multiplicative increase, because you can rewrite this as e to the b0 times e to the b1x times e to the b1. So this right here is called the odds ratio. That's what that is. Because for each additional increase, 1 unit increase in x, you multiply by e to the slope here. So this odds ratio is e to the slope the odds ratio is e to the slope, not to the intercept, to the slope. Okay? So we can see how this works on the next page. So let's just make sure we understand this. This is our line. I can't repeat this enough. This is our exponential curve. And this is the S-shaped curve right there. Okay, so this is the multiplicative increase in the odds, e to the b1x. Okay, so here, let's see. So we're going to do so again, here's the 3 forms of the logistic regression. Here's the first one we went to, the second one, and the third one. And now we're going to use this odds ratio to see how, if you go up 1 in biological science score, you're just multiplying by e to the slope. So the odds ratio is equal to e to the slope, which in this case is e to the 1.276, which is approximately 3.58. So your odds are going to get multiplied by 3.58 for each additional increase in your BS score. Okay? So for example, we already got 1.75 here for just by plugging in a 10, didn't we? Isn't that the one we? Yeah. Right here on page 203, there's the 1.75. That's what we did, those 3 steps. But now let's say we had that, and now you just want to, okay, so you go up 1 in your biological science score. Well, then all that's going to happen is you're going to take 1.75 for the odds and multiply it times e to the 1.276, or times 3.58. And I did that, and I got 6.27. Okay, well here you know how to get to the probability. This would be 1.75 over 2.75, and that's where we got that 63.6%. And now the probability would be 6.27 over 1 plus that 7.27, and here we get 86%. So that makes sense. And now let's say we wanted to go up another one, 12 to 12. Well, then we'll just say 6.27 times e to the 1.276. So that's how the multiplicative change in the odds, which is equal to 22.46. And then your probability changes from 22.46 to 20 over 23.46, which is 95.7%. You can see how it never can get greater than 1. Let's say we skip down to 14 and we just were given this, 1.75. What would we do? 1.75 times e to the 1.276 times 1.2, et cetera, and that's the same thing. We'd be multiplying by 1.276 4 times, so that's the same thing as multiplying here by 4 in the exponent. And I did that, and I got 288.2. So then what do we get? 288.2 over 289.2, and that's 99.65%. Okay? So basically that's pretty simple, and you'll see that all the time, this odds ratio right here. That's different than the change in probability. The change in probability varies and is greatest around 0.5. Okay, it's greatest around 0.5, which is probably pretty useful to you guys, because think about this. You see how right in the middle here, it makes a huge difference in terms of getting accepted. Just a slight increase in your biological science score. Think about this as like, you know, how your GPA or your GREs or whatever, people get so bent out of shape, they want to just, they might be up at the top and they think it's really important to change it just a tiny, you know, to increase it a little bit, but it hardly, look, when you're way up here, your chances of getting in are very good already, or if you're way down here, it hardly makes much difference. You're not going to get in even for a little increase, but in the middle, it makes a very big difference right here. So if you're in the middle of, for some standardized tests, the middle of those who are getting accepted, it makes a big difference. It doesn't make so much difference if you're way up here. Okay, now, or way down there. Now let's go back to what we're talking about here. All right, so given this, two people have a 2-point difference in their biological science scores. Compare their odds of getting into med school. The person with 2-point higher has a what? I should have given you another possibility. How about this one, to e to the 1.276 times 2? That would be another possibility. So there's 3 correct answers here. Which ones are they? I'll give you a minute to circle them. Well, this is what we've been doing. You know, that one's right. And that's the same thing as this one. That's the same thing as this. And it's the same thing as this, because I said right here. All right, you just multiply. For 2-point difference, you multiply, and then you multiply again 2 times. So for a 3-point difference, obviously, it's going to be e to the 1.276 times 3. And that's 45.97. Whoops, this is wrong. This is wrong. Has a not a greater chance, a greater odds of getting in. We don't know what, that's different than the probability. Greater odds of getting in. Sorry about that. Now, if 2 people have a 3-point difference, we know that their odds, we know this, odds, how do their probabilities of getting into med school compare? Well, remember, this just tells you you don't have enough information. Why? Because you know the ratio 3 times, you know the odds ratio, the ratio of 2 odds, but you don't know their odds, and you don't know their probabilities, but not the odds. If you knew the odds, well, then you'd know the probability, right? Because the probability is just odds over 1 plus odds. You don't know the odds or the probability. So remember the picture we just looked at. Remember the S-shaped curve. And also the exponential curve, the odds. Odds and probabilities change. Remember the S-shaped curve and exponential curve. Odds and probabilities change depending on x. So what would you need to know? You don't have enough information. What would you need to know? You'd need to know x. Where on that curve, or where on the S-shaped curve you are. You'd need to know x, the biological science score. They change. You know the odds ratio. That's different than knowing the odds. All right, let's see. Is that pretty much, boy, we're almost done with this, right? I think that's enough for today. I think I'm going to let you out now because we could easily do this next time, and I'll just post that. Then I can post some homework, and I don't want to make, the homework's going to be fairly short. I don't want to get too far ahead of it. So we went through this pretty quickly. Any questions on any of this? All right, and I have your, right here. Okay, so we'll pick up next time, and we'll finish logistic regression this week.